So this time I'll be talking about pre-trained sentence and contextualized word representations. So these are kind of one of the major workhorses of NLP nowadays. They use transformers a lot of the time, like we talked about last time. So that's another big workhorse of NLP nowadays. So lots of important concepts this week for general NLP methods. And so, yeah, let's get started. So as we know, we're using neural networks to do lots of different things for NLP. And what we do basically is we take in sentences, and usually we convert them into vectors, such as one vector per word. And these can be used in attention or for various other things. And some of the things they can be used for are things like word level embedding or prediction. So this could be for something like tagging, like part of speech tagging, or other things like that. We're going to be talking in more detail about these tasks next week. But they can also be used to somehow generate embeddings of the whole sentence. And this can be used for sentence level embedding or prediction. And both of these are important. Both of these can be used for kind of a broad swath of NLP tasks. And I'm going to be talking about methods to learn good word level embeddings or sentence level embeddings going forward. So the goal for today is to discuss contextualized word representations and sentence representations, and briefly introduce tasks, data sets, and methods that are used to learn these, and introduce different training objectives, and talk about multitask and transfer learning, kind of the very basics. And we're going to talk a little bit more detail about multitask and transfer learning next week as well. So to go into the very basics of what we mean by multitask learning, I'll give the obligatory nod to Bob, which is multitask learning was proposed by a CMU PhD thesis, what, 25 years ago, Rich Caruana. Oh, yeah. But yeah, so multitask learning. But the types of, I have a couple types of learning up here. And up until now, we've been talking a lot about like supervised learning, where we have an input and an output, and we train our models based entirely on inputs and outputs. Or we've also talked about language modeling, which is kind of an unsupervised learning task where we just have inputs and we'd want to model their distribution. But multitask learning is a general term for training on multiple tasks. So we're not just training to learn one distribution P of Y given X, but we might have a couple distributions like P of Y1 and Y2 given X, or we might, and this is distribution 1 and this is distribution 2, and then we might have another distribution P of X where we're just modeling the input itself. Transfer learning is a particular type of multitask learning, a very important type of multitask learning that we do a lot in NLP nowadays. And it's basically where we start with, or we have one particular task that we really care about. So for example, here P1 might be the distribution we really want to model. And we're just using the learning of the other two distributions as a means to learning how to model P of 1 better. So we kind of have a target distribution that we really care about. And pre-training, which I'm going to talk a lot about here, is a type of transfer learning. And what this is we basically train on one objective first, and then we continue training on another objective that we care about. So we might, the most common variety of pre-training is where we train on some sort of unsupervised task on lots of textual data, and then we adapt our model to learn some other variety of task. Any questions about this? Pretty good? Okay. So one of the interesting things about NLP is its level of variety. There's so many different tasks that we could be handling, and each requires a different variety of data to learn, assuming we're using machine learning methods, which we generally are. So some of them require only things like text. For example, language modeling only requires text in the domain that you're interested in. Other varieties of text require other varieties of tasks require naturally occurring data. And these naturally occurring data are data that we as NLP researchers do not need to go out of our way to create. So basically, tasks like machine translation, very often there is data that other people will be creating for other reasons. And this is good because often we can get much more of this data than the data that we as NLP researchers, have to go out of our way to create, right? And then the final variety of tasks are things where we need to do hand-labeled data, where either us, ourselves, or some other NLP researcher or engineer or something needs to hire people to do these labeling tasks. And these generally will be able to get much less data than most other tasks. And very often we might be able to get data, but we can only get it in English, for example, because whoever created the data set didn't bother to create it for Vietnamese or whatever language we want to model. And yeah, as I kind of alluded to here, this is in many we would need to get this data in many languages and also potentially many domains. So if we want to create a question answering system on Wikipedia articles might not work so well on something else like biomedical research papers. So when do we use multitask learning? Rule of thumb number one is to multitask to increase data. So we perform multitasking when one of the two tasks has fewer data. So we can do something like going from a general domain to a specific domain, like web text to medical text, high resource language to low resource language, like English to Telugu. Also plain text to labeled text, LM to parser. So like I said before, this is one of the main reasons why we would like to use multitask learning. The second one is we want to perform multitask learning when the tasks are related, because the main advantage of multitask learning is that we use the learning of one distribution to aid the learning of another distribution, especially in the case of transfer learning. And so the tasks need to be related enough that we would be able to do something with them. And one interesting example of this was particularly creative, and I think it won the best short paper at EMNLP 2016 or something like this, is they thought of two related tasks, namely summarization, summarizing text, and predicting the eye gaze of people who are reading text. So they put eye gaze measuring glasses on people and looked at where they were looking at when they were reading a text, and then they used the prediction of that to also improve summarization. And why does this make sense? The important parts of text are the things that people are going to be looking at more when they read it. So more generally, in the case of transfer learning, not just multitask learning, you want the information that you're going to be predicting in your target task to be necessary to solve the task that you're learning, the other task that you're learning. And actually, language modeling is a very good multitask learning task because it's actually pretty hard to predict the next word in the sentence or predict the probability distribution over the sentence without also understanding the sentence's syntax or semantics or topic or other things like this. So because of this, if you can learn to language model, you can also learn, at least to some extent, a lot of other necessary things that would be useful for part of speech tagging or parsing or sentiment analysis or things like that. Great. Any questions here? Okay. So standard multitask learning, the way it works is we train representations to do multiple tasks, do well on multiple tasks at once, like language modeling and tagging. Procedurally, the way we can implement this is we can have a model where we sample batches of data to do our gradient updates on, and we just sample one from one task, another from another task. There's also more complicated things like changing the sampling ratio or giving weights to these multiple tasks. I'll cover them a little bit more next week, but this simple strategy works reasonably well. There's many examples of this. The earliest example of this in kind of like neural network land is BERT and West in 2011. It's been in use for 10 years at least. And then pre-training is a very popular version of this, which I'm going to be talking about more this time, where we first train on one task and then on another. So we could train on a task with naturally occurring data like translation or language modeling and initialize our parameters and then train on a different task like tagging. And this has been used in word embeddings, sentence encoders, contextualized word representations, you name it. So next, I'm going to go through some concrete methods, but before I do, I'm going to explain why I explain the methods the way I do. And basically, recently, pre-training is kind of like a brand, or like people create pre-trained models as like essentially brands. And there's many methods with names like Elmo, BERT, Roberta, XLNet. I'm sure you've heard of at least some of these. But when you think about what these methods and also the models that are released together with the methods entail, they refer to a combination of several things. So they refer to a model, the underlying recurrent neural network architecture that's used to train them. They refer to a training objective, so what objective is used to pre-train, and also what data they are trained on. So if you're using the Roberta model, you're using a particular neural network architecture, a particular training objective, and a particular data source. So when you're saying, well, Roberta worked better than XLNet on this task, or Roberta worked better than BERT on this task, you're saying that that combination worked better as opposed to like any individual data set or objective or something like this. And in order to really understand this well, I think understanding the underlying components of each of these is also a good idea. These don't necessarily need to be conflated. In fact, there's some good papers that maybe I can introduce at the end that examine, do more controlled experiments. And I will, yeah, maybe I'll give a few examples of those too. Okay. So before I go into specific details, I've talked, basically all of NLP uses these methods nowadays. All of NLP uses pre-trained representations of some variety. We're going to be talking about like tagging and translation and other tasks like this a little bit later. This time specifically, I'm going to talk about some tasks using sentence representations. And the reason why is because this is probably going to be mostly the only time I talk about them, and then we're going to not talk about them later. So this is maybe a good place to do so. So here I'm specifically talking about sentence representations. And what I mean by this is where you basically take in a sentence and turn it into a single vector and use that for some variety of tasks. And these can be used for things like sentence classification, paraphrase identification, semantic similarity measurement, entailment, and retrieval. And sentence classification, we've already talked about a lot. You've already implemented something related to this, so I feel I don't need to explain it in that much detail. Basically, something like sentiment analysis, where we predict a label for a certain sentence. That being said, there's lots of tasks. We already talked about some of them, so that's all I'll say for today. Another place where sentence representations could be used is for sentence pair classification. So this is a very common task nowadays, used in both practical settings and just as a way to measure how good sentence embeddings are or contextualized word embeddings are. And it's basically classification over multiple sentences where you take, like, this is an example and this is another example. You throw it through a classifier and you get a yes, no decision or multi-class decision. So some examples of this are things like identifying whether two sentences mean the same thing. And this could be, for example, two sentences like this, where essentially these mean more or less the same thing. One note is that exactly the same thing is often too restrictive. So in paraphrase identification, they'll often say, you know, like the main content of the sentence is the same or something like this. So that's one type of classification task. Another type of classification task is semantic similarity or relatedness. And what this is saying is now this is no longer a binary classification that says this is exactly the same or this is totally different, but rather it's a regression task where you are taking in two sentences and you want to predict a relatedness score between them. So for example, a man is jumping into an empty pool. There is no biker jumping in the air. These have jumping here, but they mean basically very different things. On the other hand, we have a person in a black jacket is doing tricks on a motorbike. A man in a black jacket is doing tricks on a motorbike. These are virtually identical, so they get a high score. And these are often used as a test bed for how good sentence representations are, where essentially you calculate a representation of sentence A, you calculate a representation of sentence B, and you take the cosine similarity between them or the dot product between them, and you see how well it correlates with these human judgments. So I think one of the main reasons to know about these tasks in the first place is because you'll often see them in evaluations of like sentence embeddings or something like that. Another thing is textual entailment. This is also often called natural language inference. Actually, sorry, I have two questions in Zoom. Are there studies that have looked into how these individual components, architecture, objective, and data contribute to the final performance? Oh yeah, that was a question from a while ago. I'll answer that later. And then the second question is, in this context, does sentence refer to a sentence in the conventional sense? Can it be a phrase or paragraph? Oh yes, I'm saying sentences here, but it could definitely be a phrase or a paragraph. It's harder to compare the similarity between like a phrase or a paragraph because there's just more stuff in there. But yeah, it could be used to embed a phrase, a paragraph, a document, anything else like that. Okay. So textual entailment, basically what textual entailment or natural language inference is doing is it's testing whether one sentence is entailed by another. And what that means is basically if A is true, then B is true. And the woman bought a sandwich for lunch entails the woman bought lunch. So we know the woman bought lunch if we read the first one. However, note that this is directional. So the woman bought lunch does not entail the woman bought a sandwich for lunch, right? There's also contradiction. So if A is true, then B is not true. The woman bought a sandwich for lunch and the woman did not buy a sandwich. So, you know, this is not true if A is true. And we also have neutral. So the woman bought a sandwich for lunch, the woman bought a sandwich for dinner. You know, maybe it's not very likely that you do both, but who knows? She might really like sandwiches. So basically, this is a very common task. It's more commonly called natural language inference due to like the Stanford Natural Language Inference or what's MNLI? Multi-domain natural language inference data sets. And one thing is that this is something that's actually quite useful. These two tasks themselves are actually something that can be quite useful. For example, semantic similarity or relatedness can be used for things like evaluating text generation systems. So like last time I talked about, Blue or other things like this. Semantic similarity models can also be used to evaluate whether the output is similar to semantically to a gold standard human translated output. So that's one example. Textual entailment or natural language inference could at least theoretically be used to do things like verify facts. So you have a large document, you have a statement, and you want to go in and verify whether that statement is correct. So you can verify that by running an entailment system and see whether it's entailed or not. Unfortunately, in my experience, the data sets that are created for this textual entailment task don't have very good coverage, and they have some underlying assumptions that make them a bit difficult to use in practice. For example, most of the data sets are created by crowd workers where it's like, think of 3 sentences that are entailed or neutral or contradictory. And if you do that, all of the sentences end up being very similar. So it becomes not very good at judging like very different sentences, for example. So there's some issues with existing data sets and as a result, existing models for this, but nonetheless, it's an interesting task. So I had a question, are all sentences mapped to fixed length vectors in the case of these models? They can be or they cannot be. For textual entailment, actually most methods now use contextualized representations, which I'll talk about later. For things like semantic similarity, yes, it's more common to map words into fixed length vectors, take the cosine similarity, and measure that as a metric of semantic similarity. I have a question. Would using character-based sentence encoding and word-based sentence encoding produce similar sentence representations? That's a really good question. Saying similar with respect to the sentence representations is also an interesting thing, because how would you define whether 2 representations are similar in the first place? But I think word-based and character-based models have different strengths and weaknesses, and it's not necessarily the case that they would be good at both things. Like character-based models tend to generalize a little bit better to like conjugation or things like this, rare words, whereas word-based models tend to be better at common words because it's easier for them to remember whole words. So yeah, that's a good question. Okay, any questions about these? Okay, so now let's get into the methods. So we have training sentence representations. So there's a bunch of different ways to train these representations. I'm going to mainly focus on ones that use basically data that's not supervised in any way. It's naturally occurring data that you can find anywhere on the web for the reasons that I talked about before. This data can be found in abundance, so it's easy to train pre-trained models, and it's what tends to be used. So the first variety of thing, which is the most simple, is training a language model and then using it to generate a sentence representation and transferring it to other tasks. So the first example of this is this Dai and Lei paper 2015, where they basically used an LSTM model, and they had a language modeling objective. And the data that they used to train it was a classification data or additional Amazon reviews. So the classification data would be something like the Stanford Sentiment Tree Bank, which people are very familiar with. And the LM objective is just predicting the next word, like what we talked about before. So yeah, there's our LSTM. And downstream, the way they use these models was they initialized the weights of the classification model, and then they continued training. And the interesting result that they had in this paper, which I think really motivated the use of pre-training techniques, is, and it was very interesting to me, it's not something I found obvious at the time, is even training the LSTM language model on only the classification data, like literally the same data that was used to train the text classifier, they saw large gains in accuracy for text classification. So one notable thing here is they didn't actually increase the amount of data by using multitasking. They just had a different objective. But nonetheless, this greatly improved the accuracy of classification. And I think the reason for this is because the language modeling objective has to work a lot harder than the, oh, sorry, go ahead. Oh, no, they did use the classification data. They first trained on language modeling, and then they trained a text classifier after that. So they initialized the parameters and continued training. And this wasn't immediately, obvious to me that this is what would happen, but it's pretty obvious in hindsight because language modeling is a much harder task than text classification, right? So maybe you could think about text I'm slightly learning Chinese right now. I'm not very good at it, but I know the words for good and bad in Chinese, right? And so if I know the words for good and bad in Chinese, I could listen to somebody speaking Chinese and do a little bit of sentiment classification, right? But that doesn't mean I could speak Chinese or generate Chinese. And also on the really hard cases of sentiment classification, I would also fail at doing it because you need to have more nuance. You need to be able to actually understand the language. And so what a simple classifier can do is it can do word spotting. It can spot some words that are kind of indicative of the language, indicative of the positive or negative sentiment label, but it might not generalize as well because it hasn't learned anything deep about generating the language, and it's just good at word spotting things that it saw in the training data. However, if you do language modeling, you have to work a lot harder. You need to learn about the syntax. You need to learn about the semantics of the language in order to be able to generate the language. And by doing that, you're able to generalize better to new data. So even if you train on exactly the same data, that's an argument why language modeling is a good pre-training objective or good multitask learning objective here. Yeah.
Doesn't this mean that for the classification task, if your loss function or your objective is like you could basically use that and have the same results as well. So basically, right now we've broken it down into pre-training plus when we are performing classification training. So since the model is able to extract more information out of this using this training regime, is it possible to replace all of this with just a better loss function for the classification task that would heavily penalize that kind of learning?
So could we replace the like pre-training and fine-tuning thing with a better loss function for the classification task? Well, if you treat language modeling as a better classification function for the classification task, then sure, I guess you could say that that's what it's already doing. If you wanted to come up with some other loss function that didn't have to do with language modeling, then maybe, but you're losing information about like what the words in the sentence are if you just use the classification labels. I guess that would be one way to say that. Yeah. So,
but in this situation, won't we have the same problem that we have less data for the final second task? That's the whole reason why we are using weights from the first task.
Right. So what I was talking about now was even using just the same data. So even just using the same data, the LM was still advantageous. And then of course, when they added the Amazon reviews, they had much, much more data. These were Amazon review text with no classification labels. And that further much improves. So it's kind of a twofold improvement. It's an improvement of having to work much harder to do the language modeling task than just to do classification, and having more data due to this. So I think there's a twofold improvement here. Yeah.
Can we say more concretely that the language modeling objective is forcing the model to learn the position of the adjective in the sentence, trying to learn the structure of the adjective in the sentence? That's why it's
So is the language model trying to learn like the position of the words in the sentence, like adjectives or whatever else? Yeah, for sure. And it's trying to learn syntax, it's trying to learn recursive structure, semantics, anything you need to do to predict the next word properly, to distinguish between natural and unnatural sentences. And that will include things like word position and other things like that as well. Yeah. Cool. So this kind of seminal paper was followed up by GPT in 2018. So this is basically the same training objective, language model objective, but it's using a transformer model instead, and it was trained on different data. And downstream, they did both fine tuning and so on some tasks, they just fine tuned the additional, the original model. On other tasks, they trained the language model on multiple sentences for like sentence pair classification tasks and things like this. So they had some other tricks there as well, but the basic idea is still you train a language model and then you transfer it to other like tasks. Another example of a objective that you could be using is something called an autoencoder. And the reason why the autoencoder is notable is because it is a first step towards learning sentence embeddings. And here, this is a language model where it's basically learning to predict the next word. And then by the end of the sentence, you assume that you've encoded some information about the words in the sentence. But here, this autoencoder is attempting to directly encode the entirety of the information about the sentence in a single vector, and then decode the output sentence. So you have an encoder and you have a decoder like this. This was used on the same, this is from the same paper as the LM one that I talked about before. And basically what they did was they did text classification and they initialized the weights and continued training. Interestingly, this autoencoder objective did not prove quite as good as the LM objective in general for doing text classification. This is also not immediately intuitive because essentially what you're trying to do here with this encoder is encode all of the information in the sentence in a single vector before decoding and trying to regenerate the sentence. So you would think that this single vector that you encoded here was actually something that would be very, very useful downstream. However, that's not the case. And does anyone have a guess why this might not be the case? It's a little bit tricky. Yes? The question? Yeah, so the question is, it is not the case that this autoencoder is necessarily better than just training a language model to predict every word. However, you might think that the encoder, because it encodes all of the information that you need to decode the sentence here, might result in a better kind of sentence embedding than the thing that I just showed here, where you're training a language model to predict every word. Because here you're just training a language model to predict every word, and whatever you have in this vector here is kind of like whatever's left over, or yeah. Mm-hmm. Yeah, so when you're trying to reconstruct the sentence, it might be trying to focus a lot on the syntax, and the syntax might not be useful for downstream tasks. I think that's potentially one reason. It's not exactly the reason that I was thinking about, but yeah, sure. Yeah. So to reconstruct the sentence, it would have to encode all of the information from the previous sentence, but to do classification, you'd have to have only a few keywords. Maybe that might be the case. It's actually maybe flip it on its head a little bit. I see a question: is the Ray Mooney quote fitting here? That's actually a potentially a good point, although that's kind of a criticism with all sentence vectors. Yeah.
Very brief aside. I mean, the Ray Mooney quote. You know, there are words like World War II that have a lot of semantic content too, right? So it's not clear to me that the average sentence. That's a problem, right? Yeah. You know, words have a lot of content too. Yeah.
I agree. And so I see, sorry, one other question. Is it related to the decoding path link issues that we talked about last time, or that we need to maintain global information rather than information specific to the time of the classification? So the decoding path link thing is like, there's a very long path between here and here. Because of that, it's not able to learn gradients due to like vanishing gradients. I think this is the closest of the answers that I got. So I'll call that right. Congratulations, good idea. Like, I think all of the other things that people said are not unreasonable. Somebody is maybe accidentally writing on my screen, so it'd be nice if you would not do that. Thank you. I don't know how to stop it. Maybe I shouldn't admit that I don't know how to stop it, because then we might have more problems. But yeah, basically, one interesting thing about autoencoders is that autoencoders, in order to produce the remainder of the sentence, there's two ways you can do it. One way you can do it is memorize all of the info. And the other way you could do it is by just looking at the previous word and using the previous word to guess what the next word is, because you see you're feeding in the previous word here, right? And because of that, if you think about the decoding path, would it be easier to have Z look at Y and say, oh, Z is a word that commonly follows Y, so I'm going to predict Z? Or would it be easier for Z to back propagate all the way back to Z here and say, you know, well, I saw Z like 50 words ago, so I'll probably see Z here. And basically, I think the answer is the decoder is essentially, if the decoder is too strong, then you're going to be less likely to get an informative representation here, because the decoder can like basically live on its own and not worry about those things. So there's actually some papers that examined this. Since I took a lot of time on this, there's some papers that examined this in more detail. This is one example. Improved variational autoencoders for text modeling using dilated convolutions. And basically, the idea behind this paper is that they took the output side of one of these kind of autoencoder models, and they made that decoder weaker, and that resulted in learning a better hidden representations. So that's kind of empirical evidence that this idea is correct. So basically, it's an interesting, this was an interesting idea, but this is not super widely used now, and most people focus on language models. However, one thing that is widely used and also was kind of reflected in BERT, in BERT's training objective, is this idea of skip thought vectors. And basically the idea, this is a paper that I believe Jeff Hinton was also a co-author on, and he always comes up with very nice names like skip thought vectors. And the idea is you have an LSTM, you encode the sentence, and instead of re-encoding your current sentence, you try to encode the surrounding sentences, and you still suffer the same kind of issue of this being an autoencoder. But in order to encode the surrounding sentences, it becomes a less kind of trivial task of repredicting the like the first word that you've already seen. And because of that, you need to learn a little bit more high level information, like what is the topic of the sentence, or what is the general discourse, what is the tone of the sentence. And because of this, this was a pretty widely used method for a while. Great. Oh, and the way this was used downstream was they fed this into a basically predictor that used like the difference between the embeddings or the embeddings multiplied together, et cetera, to do like word pair classification, sorry, sentence pair classification problems, other things like that. Another method that is very effective at learning paraphrasing based metrics like sentence similarity is paraphrase-based contrastive learning. And what I mean by this is basically the objective is to predict whether two phrases are paraphrases or not from a data source like the paraphrase database. And I think this is a really useful idea in terms of learning actual paraphrases, because if you think about most of the other objectives that we've talked about so far, you wouldn't have a really strong motivation to distinguish between, for example, named entities. Like if I say, well, I met John at the store today, or I say I met Jane at the store today. The following sentences in a language model are probably not going to change a huge amount. Maybe they'll change a little bit, but not a huge amount. If I pick two proper names that tend to be the same gender and the same ethnicity, it'd probably change even less, right? However, those words are very different. And if you had a machine translation system that translated John into Jane, that would be a problem, right? So what this method does is basically it has a gold standard list of paraphrases, and it tries to identify which phrases are actually paraphrases of each other and which phrases are not paraphrases of each other. And this can be used downstream for like sentence similarity, classification, etc. One other interesting result that actually has held in follow-up research is LSTMs or transformers or more complicated models tend to work really well when you test them on in-domain data. But if you have out-of-domain data, even simple models like averaging together word embeddings are pretty competitive. You could also create large-scale data for paraphrasing. And basically the idea is you get a large parallel corpus, translate the one side of the parallel corpus using a neural machine translation system, and basically do a little bit of filtering, and now you have a huge corpus of sentence level paraphrases that you could use to train a model like this. So this results in a very large corpus, like 30 million translations, 30 million paraphrases. Okay. I had one question that I missed until now. So does the word order matter for autoencoders? Yeah, I think if you flip the LSTM in the reverse order, it might make a little bit of a difference, but probably not a huge difference. I think the same fundamental issue of the decoder being sufficient to learn representations is probably still there. Okay. Another thing that is rather interesting and still useful nowadays is entailment plus transfer. And basically the idea is, as I mentioned at the very beginning of class, one of the big advantages of multitask learning is that it gives you the ability to use a lot of unlabeled data to train models. However, one disadvantage of any learning algorithm, I would say, that is based entirely on raw text is some phenomena are very important, but extremely rare in raw text. So some examples of this might be the necessity to model very long distance dependencies in text. So if you have a big document, you might have one or two words that are not easily predictable from the immediate context. But most of the words you can predict just by looking at the current sentence or a few words back. So because of this, language models don't tend to be really good at modeling long distance context. Another thing they don't tend to be good at is modeling, unusual expressions. Like, for example, if you have a question, yeah, actually there was just a paper, there's just a paper at ACL about this. Which linguist invented the light bulb presupposition verification for question answering? And the idea is a language model might have seen lots of questions in its training data, but it's very rare to see a question where the answer is I don't know, or silly, a linguist did not invent the light bulb. So because of this, no language model would be able to correctly answer that because it very rarely sees it in the training data. So anything that you don't see in the training data might not be a good candidate for something that you want to learn through multitask learning. And so the idea of here, this entailment plus transfer method is basically, we have a big corpus for textual entailment. Like one example of this is the multi-domain natural language inference corpus, where we have lots of human created data that aims to verify like the logic, the ability of models to capture logic or entailment or other things like this. And because this is rarely tested in training your language modeling objective, you would do well by training on this data and learning sentence embeddings from it. So basically what they did was they swapped in the objective and it's supervised training for tasks such as entailment. And you might think this would work better because this task is more difficult and requires capturing nuance, capturing logic, other things like this. But if the data is much smaller, then maybe this would not work as well. So basically what they found is using a bi-LSTM plus max pooling model and training on Stanford NLI, multi-NLI, this tended to be better than unsupervised objectives, such as the skip thought vectors, despite the fact that it was trained on much, much less data. So I think this is also a very interesting finding, which basically tells you don't necessarily throw out your supervised objectives just because we can get billions of sentences of training data in unsupervised objectives. And this actually still holds nowadays as well, despite the fact that this is from 2017. I can show some examples later. So one kind of modern toolkit that you can use for doing, sorry, go ahead. Sure. So the question that they basically asked was, does supervised training for a task such as entailment learn generalizable embeddings? And the potential answers to that question are because the task is more difficult and requires capturing nuance, the answer might be yes. Or because the data is much smaller, the answer might be no. So basically, they tested this hypothesis in this paper here, and they found that in general, the infracent embeddings that they trained from the NLI tended to do better than unsupervised objectives, basically. Oh, the data that they can use to train the embeddings based on training using entailment or inference is much smaller because they can only use manually and labeled data from like these data sets, for example. So if you want to use sentence embeddings nowadays, there's a toolkit that's pretty widely used and well-maintained called Sentence BERT. Or it was called Sentence BERT. Now it's been renamed into Sentence Transformers to make it more generalizable. It contains a whole bunch of training objectives. For example, it contains embeddings that were trained using the unsupervised BERT objective. It contains embeddings that were trained using kind of like paraphrase-based contrastive learning or directly regressing to try to solve sentence similarity tasks, et cetera, et cetera. So it's kind of like a one-stop place to get lots of models that you could use for these. It also has some multilingual models as well. Yes?
Ideally, shouldn't we use all these objectives to learn the ideal embedding?
Yeah, could you use all of these objectives to learn an ideal embedding? I think the answer is you probably could, and if your model had high enough capacity, that's probably ideal. As far as I can tell, it's not super common to actually do this. Maybe it's just more engineering work or things like this, but usually people mainly focus on a single objective. So hey, maybe that's a good thing to try out, at least in the fine tuning of training objectives. Yeah. Okay. So I will move on to the next part. This is also an important part, so I definitely want to cover it. It's on contextualized word representations. And contextualized word representations are basically, instead of one vector per sentence, we have one vector per word. And these can be used in many different ways. Like one way, for example, would be to calculate one representation for each word here, one representation for each word here, feed these vectors into a classifier and say yes, no. You could also use it for tagging, whatever other task you want. So how do we train this representation? So the first attempts to train representations like this that I'm aware of anyway are Context2Vec and Elmo. Or Context2Vec is the first one, and Elmo was kind of the one that popularized this. And basically the idea is you have a bidirectional LSTM. And what it does is it's basically a language model, but you train it in both directions. So for this language model here, you would feed in the first word, and you would feed in into the forward LSTM, you would feed in the later words into a backward LSTM, and then you would, in the middle, you would predict the word that's kind of missing here. So this is a bidirectional prediction objective. This was trained on 2 billion word corpus and used for lots of things like sentence completion, word sense disambiguation, etc. The results were actually pretty convincing, and this kind of spurred interest in this idea of contextualized representations. Elmo, however, was what made this method very popular, and it's basically a multi-layer bidirectional LSTM. It was trained in a slightly different way. It was trained to predict the next word left to right and the next word right to left. So it's basically just two bidirectional language models trained independently. And it was trained on a 1 billion word data set. And one interesting thing is how you use the vectors. So you can either use the vectors as is, or you can fine tune the whole model to do the downstream task. Elmo did something that was a little bit in the middle. And basically it took the layers of the LSTM and it learned a linear interpolation between the layers and then used them downstream for the downstream task. And the idea behind this is there have been some results on pre-trained language models that show that different layers capture different traits. So for example, the earlier layers capture things that are more like syntax, and the later layers capture things that are more like semantics, basically. So by learning this linear interpolation, a syntax-based task might want to use the earlier layers, or might put more weight on the earlier layers. A semantics-based task might put more weight on the later layers. So that's how Elmo was used downstream. So that's kind of a historical note. These aren't used as much anymore, and but they led into the masked word prediction or masked language modeling objective that is used in BERT, and this is kind of the bread and butter of representation learning nowadays. So the way this works is you basically have a transformer-based model, a multi-layer self-attentional model using transformer blocks, and you input a sentence or a pair of sentences, and you append an extra token called CLS, the CLS token, and you also have segment embeddings. So this is kind of like what we talked about last time. We have the token embeddings, and the token embeddings can have, for example, multiple sentences. So you'd have a separator between the multiple sentences that you're handling. And you also have this CLS token here at the very beginning. And you also have embeddings of like which segment you're in. Are you in segment A or segment B? It also uses a subword representation. Basically, long story short, what a subword representation is where we divide low frequency words into multiple pieces like this. And I think Bob is going to talk more about this later. And the objectives that it uses are twofold. It's using masked word prediction and next sentence prediction. And I'll talk about both of these. And this was trained on the books corpus in English Wikipedia. So masked word prediction, basically what you do is you mask out a word in the input. And then you try to predict the word that was masked out. So what does masking mean? It means basically replacing the word with something else. And in BERT, 80% of the time, this word is substituted with the input word with a special token called mask, which basically says, I don't know what this token is. 10% of the time, it's substituted with a random word. And 10% of the time, it is there's no change. So you just keep the original word. And this is done for 15% of the words in the input. These numbers sound arbitrary. I'm sure they're not arbitrary. They were certainly tuned by the authors of BERT to get this to work well. But basically, just to reiterate, we do this masking process for 15% of the words. And then after we decide to do the masking process, you have this sort of proportion. So in a way, this is very similar to the context objective. You're basically looking at context on either side, and you're predicting the word in the middle. However, this is more suited for self-attention. And the reason why is because if you do the context objective, you basically would have to, you'd have to prevent the word from ever, you basically have to like have a right side and a left side, and the right side and the left side couldn't interact with each other in any way. But if you just mask out the input, the right side of the word and the left side of the word can interact with each other through all of the layers of the transformer model. And that makes it both more effective at encoding the surrounding context and easier to implement, because all you have to do is you have to flip the like the input, and pass it all the way through, all the way to the top. So that's the masked word prediction or masked language modeling objective. Oh yeah. Oh, sorry. So the 80% substitute input word with mask is basically like you're trying to guess what you're missing there, right? You're trying to fill in the blank. The substituting the input word with a random word is basically, you might almost look at the following two together or something like this. The substitute the input word with a random word and no change. Substituting an input word with a random word, you're basically trying to denoise the input and predict what word you should have in there. The no change thing is basically if you only were predicting, words in the case where some perturbation has been applied, you wouldn't need to pass the identity of the word itself to the end. You would know that the word itself is always wrong, right? So you could completely forget the identity of the actual word. But here, because 10% of the time it is actually correct, that's much higher than any other random word will be. So because of that, passing the identity of the word through is still important. So that's the motivation. Was there a criteria to choose 15% of the words from the corpus to be for masked word prediction, or are they chosen at random? They're chosen completely at random. There is some work on language model pre-training that prioritizes certain words, like prioritizes entities, for example. And you can show that by doing this, you get a model that's better at predicting entities. There's also words on kind of adapting these language models, work on adapting these language models to new domains, where you can try to pick domain-specific words and mask them out to make training faster. But in general, it's done at random. Yeah, back first. Yeah. Do you need a separator token if you're already adding segment embeddings? That's a good question. They do seem kind of like redundant in a way, but that's what they did in BERT. I think one advantage of having the separator token here is if you wanted to do like a prediction over each sentence, having the end of sentence here, token here is useful because you could grab that representation. But yeah, I actually don't have a very deep intuition about that. Yeah. Oh, comparing BERT with Elmo, what is the difference? So Elmo is actually closer to, it's closer to something like GPT. So GPT was a model where you trained a language model from left to right. Or the original language model paper that I talked about, it's a thing where you train a language model from left to right and then use that downstream. Elmo trains one language model from left to right and another language model from right to left completely independently, and then uses those representations by concatenating them together. What BERT does is it encodes the whole sentence bidirectionally using self-attention. So all of the representations from the output of the first layer onward have information about all of the other words in the sentence. So there's no limitation that some of the representations only have information about the right words and some have information about the left words. So I think that's a really big difference, and that's there's an ablation in the BERT paper that shows that this is actually pretty important for getting good accuracy. So was the CLS token initially just intended to be a beginning of sequence marker? Actually, no, and I will get to that next. So basically, one other objective in the BERT objective is a consecutive sentence prediction objective. And what it does is it classifies two sentences as being consecutive or not. So in this case, we have a classification token, and we have the man mask to the store, and then we have penguin mask our flightless birds. And then we have the man went to the store, went to mask store, and he bought a gallon mask milk. And in this particular case, the answer is that these are consecutive, and here the answer is that these are not consecutive. And importantly, when making this decision, they use the CLS token as the input to the classifier. And the reason why they use the CLS token as the input to the classifier is now for any sort of sentence prediction or sentence pair prediction task, then it would make sense to use the CLS token because it's been trained to do sentence pair prediction during the pre-training objective. So that's the basic idea behind the CLS token. There's different ways that you could do sentence classification with BERT. You could use the CLS token as is, or you could take the average of the BERT embeddings and do a classification based on the average of the embeddings or the max of the embeddings or something like this. Actually, it's more common to use the CLS token, but it's sometimes more competitive to do the pooling over the embeddings. So if you want to try it, you could try both and see what happens. Yes. What does it? Oh, so what does the CLS token represent? It's an arbitrary token that they concatenated to the beginning of the sentence during BERT training, but due to the way they trained, so it's concatenated to the beginning of every sentence, basically. So it's always there. But because they designed the consecutive sentence prediction objective like this, this objective encourages the CLS token to encode enough information about the sentence to at least distinguish which sentence is next and which sentence is not next. So that's the basic idea here. Instead of using a mask token, can word dropout be used? If not, why is the mask token important? Is a question from Zoom. And the mask token, I guess using word dropout would be very similar to using a mask token. Word dropout would maybe set the mask token to be all zeros, and they would be equivalent. So I don't think there's a major difference between them, basically. I see another question. I've also seen the n-1th layer of BERT used as embeddings fairly frequently. What's the reason for dropping the last layer? So this is a really good question. I believe in the BERT paper, they actually have an ablation with respect to this, like which layers should be used for classification. And there's something like taking the average of the last 4 layers is good. Or something like this. There's actually, I wasn't planning on talking about this until later, but maybe I'll talk about it now. There's a really great paper called BERT Rediscovers the Classical NLP Pipeline. And basically what this is showing is it shows a lot of different things, but like one thing in particular that it shows is what layers of BERT are optimal for solving different tasks. And this is one example where basically let me see. I don't actually remember exactly the details of what all of these are, but I think basically the idea is the light purple is let me see if I can get that real quickly. So they I believe they learn a weight over the layers where they attend to the representations in each of the layers, and they try to find which layers are kind of like ideal for solving each task. And they have a couple ways to do this, but basically, long story short, both ways look more at earlier layers for tasks that are kind of more syntactic, and more at later layers for tasks that are more semantic. So basically, what you can see is as the representations are passed through more layers, BERT does a better job at extracting kind of like higher level concepts, or I don't know the best way to say it, but higher information about more complicated concepts in language. Cool. So any questions about this? Yeah. How can you tell if model objectives during pre-training are interfering with each other? That's a really good question. So the simple answer is if your downstream task performance that you care about goes down, then that's an issue. There are ways to tell that tasks and multitask learning are interfering with each other, like measuring how well the gradients are aligned and things like this. But I don't know if that would be answering the like implicit question, which is like, does having two objectives like cause your model to not be learned as well? So I think that's a good question, though. I don't have a very like clear answer. So I'm going to go through a few more examples. So I think a lot of people might have heard of Roberta, and Roberta is another model that came out after BERT. It's basically the same as BERT, but it was actually, I think, I'm trying to remember if this is right. I thought they actually had more data, but maybe I'm wrong about that. But basically what they did was they did hyperparameter optimization for BERT. They trained it for longer and did a few other small tweaks, and the results are much better. So basically the conclusion here is that the authors of BERT should have trained their model for longer, and then everybody would have been happier. If you're going to use BERT, you might as well use Roberta. And there's also a lot of other new methods that have come out as well. I'm going to present a few kind of like interesting other examples. So for example, Electra. Electra, the idea here is that instead of training a model to do mass language modeling, you're training a model to discriminate between fake generated text and actual like same as original text. So if we have the original text being the artist sold the painting, and we have a sample that says the artist sold the car, this model would be trying to predict whether the text is original or not original. And so they use the same data as BERT or XLNet, which I'll explain next. And one thing they found here was that training this model was much more efficient than training BERT. And I think one of the reasons why is because BERT only calculates the loss over 15% of the words, over the sampled 15% of the words, whereas this is calculating the loss over every single word in the sentence. So it's not throwing away most of the words in the sentence. Yeah. And the generator, yes, I believe it's fixed during training, and it's also a weaker model. They intentionally made it a little bit weaker so it would make mistakes in generating some of the time. So it wouldn't necessarily just get the answer right every single time on the. It's like a weaker version of BERT, basically. Yeah, it could very well bring bias to the discriminator. It would bring bias to the discriminator in the types of things that the discriminator was most needed to be most sensitive to. But yeah, you could certainly consider doing something like that too. Cool. So another model, XLNet, is kind of interesting in that it brought longer context. It also has a permutation-based kind of like autoregressive objective, which I think is interesting, but maybe it's not super widely used now, so it's maybe not super important. But what they do is they basically sample the ordering with which you make predictions. So you're not always making predictions from left to right, but you also make predictions from like right to left some of the time. So that allows you to model in both directions. This was trained on much more data, but I think most interesting thing here is that they include longer context. So they don't just model like individual sentences or sentence pairs, but they can actually model like full documents and things like this. And I'm not going to go into the details much here in interest of time, but we'll talk more about that later. Another thing is pre-trained models are very nice, but they're also very, basically larger models tend to get better performance. Oh, sorry, go ahead. Mm-hmm. So basically, yeah, I could go into more detail, but I'll just do it very briefly right now, which is, we talked a little bit about truncated backpropagation through time, where basically you calculate the states of the previous sentence, and then you pass them on to the next sentence without backpropping into them. They're basically using a technique like that, but for transformer models, and it's called Transformer XL. So what you do is every previous time you calculate the states of the previous sentence, and then you pass them on to the next sentence without actually backpropping into them. So, and they're not actually using sentences, they're using like blocks of 128 or 256 words or something. But that's the basic idea. Cool. So one problem with pre-trained models is they can get very big and ponderous to use in deployment. And so there's been a lot of work on making them smaller. Two representative models here are Albert, where basically they look at two ways to do this. One is making the embeddings of words smaller, because the word embeddings actually are a pretty large portion of the embedding of the parameters in the model. And they also do parameter sharing across all layers. So all of the layers share the same parameters. I was actually very surprised when I saw this work. So it's kind of counterintuitive. You would think the layers would have to have different parameters, but it does. Another thing is DistillBERT. And basically the idea is they train a model to try to match the distribution, a smaller model to match the distribution of regular BERT. So instead of predicting like a single word in the masked position, like if the word was penguin, instead of predicting penguin, they would predict the distribution that BERT generated there. Okay, so finally, which method is better? Which model is best? For example, some work has found that simple word averaging is more robust out of domains. The BERT paper compared unidirectional and bidirectional transformers, but they didn't compare to LSTMs, perhaps for performance reasons. I think now basically everything uses transformers, partly for efficiency purposes, because to do pre-training, you often want to train on very large data sets. So I think that's the main reason why. However, there's not like a comparison over the many different flavors of transformers we have nowadays. So it's not really super clear. The XLNet paper did ablations where similar data to BERT was used and improvements were shown. So the XLNet method seems to be pretty good. Which training objective? there are some examinations into this. All of these are in the references, by the way, so if you find them interesting, you can take a look closer. Zhang and Bowman control for training data and find that bidirectional LMs seem better than MT encoders. The next sentence, Devlin finds the next sentence prediction objective to be a good complement to the LM objective, but the Roberta paper actually didn't find that result. So, and another thing is which data should you train on? So there's a paper by Zhang and Bowman that finds more data is better. I actually forgot to add this paper to the reading list this time, but there's also a very nice paper. Called Learning Which Features Matter. Roberta acquires a preference for linguistic generalizations eventually. And they have a comparison over different data sizes where they do some controlled experiments that basically show that as your training data gets larger, the model learns to generalize better. And we're out of time, so I won't go into the details of this experiment, but there are some examples of like controlled experiments where you control for the size of training data and things like this. So with that, I think we're a few minutes over, so I'll finish up here, but I'm happy to take any questions up front if people have any follow-ups.